All right, folks, this is lesson 5 in the bonding unit. We're going to talk about what is something called resonance structures and formal charge. I do have other videos in the links section in the content library for the bonding unit that review this as well. So if this, explanation is a little janky for you, you're a little jammed up, there are a couple good videos that I did put in the links section. The Khan Academy videos for this whole series are pretty good, and then I have broken down specifically a couple about this concept. So we've already looked at how to put together like the method for drawing Lewis structures for compounds and telling if a molecule is polar or nonpolar. So this was, count all the valence electrons, make your skeleton structure, connect them with bonds, and make sure everything, adds up. By the end of this lesson, we're going to look at something called Lewis structures for compounds that have what are called resonance structures and determine which resonance structure is the most favorable, and also look at bond order. We're also going to do formal charge, which is related to resonance structures, but it's very, very easy. Okay, so if I asked you to draw the Lewis structure for the nitrate ion, let's go through our method here. Nitrogen has 5 valence electrons. Each oxygen has 6, and then it has a negative charge, so we need to add 1 more. So here's 5 plus 18 is 23, plus 1 is 24. When you draw this out, nitrogen, oxygen, 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 we start by connecting with bonds, so that takes care of 6, right? I have to put 18 more in. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So right now I'm out of electrons, right? I have 24 electrons in my picture, but the problem here is that nitrogen does not have a completed octet, and nitrogen must have a completed octet. So if you run out of electrons, the rule is if you run out of electrons and your center atom still doesn't have a completed octet, you've got to double bond somebody. So if I take these electrons and swing them over, let me erase them from here and put them in here as a bond, I still have the same number of electrons here, right? I still have 24 electrons. Everything has a completed octet. But why would I choose to put the double bond here? Why wouldn't I put it here? Or why wouldn't I put it here? That's the concept of resonance, okay? So there's sometimes there are different possibilities to make your Lewis structure in a correct way for a particular substance. So it looks like there's going to be 2 single bonds from nitrogen to oxygens, and then that last oxygen will have a double bond. When scientists actually study the molecular composition of this particular substance, though, what they find, and they can analyze the lengths of bonds to kind of determine if they're single or double bonds, what they determined is that the bond length between these nitrogens and these oxygens does not agree with 2 single bonds and 1 double bonds. They find that the bonds are all actually the same length. This is called resonance. There's no real reason to pick this oxygen to have the double bond over any of these other oxygens to have the double bond. So what kind of happens is the true structure of this nitrate polyatomic ion is like a hybrid of all 3 of these. So if I kind of overlaid all of these structures onto each other, I have this blending in bond length between what would be a single and a double bond. Okay, so a resonance structure is invoked when there's more than one valid Lewis structure that can be made for a molecule, and this is the case for actually a lot of polyatomic ions. The resulting electron structure of the molecule, so the real structure, is given by the average of the 3. So the placement of the valence electrons will change, but not where the actual atoms are. So they're still going to be arranged. That nitrate ion is still going to be arranged in this sort of way. But instead of having a double bond, in one particular location, Each of these bonds, because there's three of them, right? There's three oxygens bonded to that nitrogen. Each of those would have a bond length of approximately 1.33, right? 1 1/3. They kind of divvy up that double bond and distribute it amongst the three of them. Okay, so instead of saying single bond, double bond, we would take that like double bond and evenly distribute it among all three of those. Okay, usually we would represent resonance structures by double-headed arrows. So if you had to, and it'll usually say it in a question, it'll say like, draw the Lewis structure for the nitrate ion, include all resonance structures. And right there is telling you like, oh, there's going to be resonance structures. So what you would do is you would draw all three of them like this. You get the idea. And then you make your third one, right, with the double bond in that third spot. Oh, the pain in the butt. It's actually pictured on the prior slide. But you would draw all three of them and draw a double arrow, you know, connecting the structures. And that doesn't mean that like they're morphing into each other. It just means that they're all equivalent possibilities. Okay, so the actual structure is an average of those three possibilities. So what resonance does is it fixes the localized electron model that we use. So it's the Lewis structure model that we follow, right? It's counting the valence electrons, putting it together. It works in a lot of cases, but not because it's like, oh, these electrons belong to this particular atom. But it's not really true, because what really happens is the electrons are delocalized. So the electrons are able to flow across the surface of the entire structure. They're not like locked in place here. So these electrons can migrate around the three oxygens, giving it this blended view. This is so cool. Okay, experiments show that nitrate ions don't have any double bonds. It has all single bonds with bond length and strength between that of single and double. So the correct Lewis structure of nitrate is not given by any one of those three, but by the superposition or the averaging of all three. This is the video on resonance structures. It's linked in the link section. So here's another example. If I had to make N2O4, so the nitrogens would be bonded to each other. So I have to have 34 electrons here. Each nitrogen has 5 times 2 is 10. Each oxygen has 6 times 4 is 24. So I need to have 34 electrons in my picture. So here's the skeletal structure of it without any, just starting out the basics, right? I put my nitrogens, I bond them together. I put my oxygens around the perimeter. So right now, 1, 2, 3, 4, 5 bonds have been drawn in. So 10 electrons are drawn. I have 24 electrons left. So I fill in my peripherals, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So I'm out of electrons, but my problem here is that this nitrogen only has 6 electrons. This nitrogen only has 6 electrons. So if I've run out of electrons and my center atoms don't have a completed octet, I've got to swing electrons in to make double bonds. So I could put this here and make a double bond, which is what is shown there. I could take these and swing these over and put a double bond here, which is what is shown there. But like, why would I choose that location? Why wouldn't I choose them diagonal from each other, which is what is shown in the second one? So because there's different possibilities here, and really there's not 4, like I could flip this over and just put those doubles in the bottom spot, but I wouldn't draw another resonance structure for that. Same thing here, I can just like flip this molecule over and reverse their locations to here, but I don't have to draw that one. You can, it's not wrong. But you definitely would want to show these possibilities. So in actuality, these double bonds don't exist in these particular spots. So I have 4 locations that these 2 double bonds are spread across. So each of these locations would have a 1.5 bond length. So let's look at ozone. So ozone molecule's O3, so 6 valence electrons per oxygen times 3 is 18. So I'll start by just connecting them in a row. I'll connect them with bonds, so that's 4, so I have 14 left. Complete the octet, so that's 12. So I have 2, right, 2, 12, 14, yeah, 2 more electrons left, and I would put them on the center atom. So I'm done with drawing electrons. I have 18 electrons in this picture, but the problem is that center oxygen only has 6 valence electrons. So I could choose to swing these over and double bond it, or I could have chosen to swing those over to double bond it. So there would be 2 different resonance structures for ozone. I have this possibility, or I have this possibility. Both of them have the 18 electrons that are required. I've just flopped the position of the 2. So in actuality, the bond length of these bonds in an ozone molecule, it's not single bond length and double bond length, it's actually 1.5 a piece. So there's 3 bonds that I'm dividing over 2 spots. There's where I get the 1.5. Right here's 3 total bonds dividing over 2 locations to get me the 1.5. And this is showing it here. Okay, observe, yeah, the true observed structure of ozone, both oxygen-oxygen bonds are the same length. And they both have that like part in between bond length. Ta-da. There it is again. Here's just another explanation, kind of like a blending. Green is a synthesis of blue and yellow. Ozone is the actual structure of an ozone molecule is in between those 2 resonance structures. So that's the idea behind resonance. So again, you're not moving atoms around, okay? You're not moving their spots. You're just floating the double bond into different locations, showing that there are different correct possibilities here. Some molecules have resonance structures that are different from each other, and you can actually determine which structure is better by using something called formal charge. Okay, and I do have another video linked about formal charge. They're all short, they're like 6-7 minutes each, but I want you to have an understanding of it because it usually shows up as like an extra point somewhere in a question. The way that you calculate the formal charge can be determined for every particular atom that is in a molecule. You have to remember VBD, okay? The number of valence electrons that particular atom possesses on its own, minus the number of bonds that it has drawn attached to it, minus the number of dots that are drawn in the structure around that atom. Okay, so formal charge is valence electrons minus the number of bonds you've drawn, minus the number of dots you've drawn for a particular atom. So when you look at formal charge and you calculate the formal charge on each particular atom in a molecule, you can determine like which of the molecular structures is most likely to occur. So you need to know the number of valence electrons for each atom, the number of bonds you've drawn in the molecule, the number of lone, non-bonded electrons, just said that. Okay. So for the sulfate polyatomic ion, there are different possibilities here. So I'm going to show you how these 2 structures were derived and how these formal charge numbers were acquired, okay? So sulfur has 6 valence electrons, each oxygen has 6 and there are 4 of them, and then I need 2 more electrons to give this ion a -2 charge. So I have 24 plus 6 is 30 plus 2 is 32, okay? So I'll start out by putting the sulfur in the middle, put the oxygens around it, connect them in. Okay, so that's 8. So I want to fill in 24 more electrons to get my 32. Okay, so that's one possibility. Another possibility, because sulfur, and this happens because sulfur has the ability to have an expanded octet. Sulfur is a third row element, so it can have more than 8 valence electrons. Okay, so that's where this other structure comes from. So this structure is not wrong. Like mathematically, it's fine because I look at if I do my electron count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have the proper number of electrons. Oxygen, none of my oxygens have exceeded their octet. My sulfur has, but it can because it has the possibility of a D sub level. So if you can, no, I don't know who in their right mind would be like, yes, that looks totally normal. Like you'd probably just go with the simplest version, and usually that's the right version. But if you are asked to evaluate, like if you were presented with both of these structures and you were asked to evaluate which one is the correct structure, you would use the concept of formal charge. Okay, so formal charge is equal to the number of valence electrons minus the number of bonds minus the number of dots. So in this first example, that center sulfur, to calculate its formal charge, sulfur has 6 valence electrons. Of its own, just a regular sulfur atom has 6 valence electrons, right? It's group 16. Subtract the number of bonds you have drawn around that sulfur. I have drawn 4 bonds around that sulfur. Does this sulfur have any dots attached to it? No. So the formal charge for that sulfur is +2. Okay, that's where you see it in this picture down below. Now, for each of these oxygens in this model up top, because each of these oxygens is identically bonded to the sulfur, each oxygen would have the same formal charge. So oxygen has 6 valence electrons on its own. It's in group 16 as well. I have drawn 1 bond for that, just evaluating one oxygen at a time here. I've drawn 1 bond, and I have 6 dots, right, around that oxygen, which gives each of these oxygens a -1 formal charge because all of these oxygens are identically bonded to the sulfur. So that's where those -1s are coming from. Okay? Now, looking at the example diagram on the left, the sulfur has 6 valence electrons. I have drawn 6 total bonds around that sulfur. 1, 2, 3, 4, 5, 6. And there are no dots around that sulfur, so that's a 0 formal charge for the sulfur atom. Now, because these oxygens have been bonded non-identically to the sulfur, the formal charge on these 2 oxygens would be different than the formal charge on these 2 oxygens. It's obvious you can see they're bonded differently. So the oxygens that I have bracketed in black, 6 valence electrons minus 2 bonds for that one of those particular oxygens minus 4 dots is 0. The oxygens that I have bracketed in yellow for one of those oxygens, 6 valence electrons minus 1 bond minus 6 dots gives me a -1 for each of those. Okay, so that's where I'm assigning those numbers that are in red. That 0 goes to the sulfur. Okay, so why am I picking this one on the right versus the one that's on the left? In a molecule, you want to get formal charges as close to 0 as you possibly can. Another thing that has to be considered is the sum of all of the formal charges on all of the atoms in the particular substance must equal the overall charge on that species. So for those sulfates, you had this possibility where these were each, well, this was a 0. These were each 0s. And these were each -1s. So yes, the overall, if I added all these formal charges together, it would add up to -2, which is the charge of the sulfate ion. And the same thing would occur here in the option that I did pick. Because the sulfur in the center, the 6 minus 4 minus 0, that gave me a +2. And each of these oxygens, 6 minus 1 minus 6, gave me a -1, -1, -1, -1. So all of those formal charges also added up to -2. But when we come to evaluate it, you always want to obey the octet rule first. Okay, so if you have an option where everything's obeying the octet rule, the sum of all the formal charges add up to the sum on the species. So if it's a neutral molecule, everything adds up to 0. That's one you want to pick. You also want to find one where the most electronegative atom has the most negative formal charge. So in this first example, I mean, between sulfur and oxygen has a higher electronegativity value, right? It's higher up in that group. So the fact that these, in this left-hand diagram, that these oxygens have a 0 formal charge and the sulfur also doesn't really make sense. Whereas the diagram on the right, the most electronegative elements, the oxygens, have the most negative formal charges as compared to the sulfur. All right, so let's look at a couple examples here. So this xenon trioxide one, right? So looking at the valence electrons here, xenon has 8, each oxygen has 6, times 3 is 18. So 18 plus 8 is 26 electrons in our picture. Now xenon is a large noble gas. It can expand its octet. So there are different possible structures for this molecule. So there's 3 presented here. They all have 26 electrons in them. Now, in just looking at these structures, like I would hope that you'd pick the one that just kind of looks the nicest because appearances are everything. But if we look at formal charge here, look at the first example. So xenon, 8 valence electrons, minus 3 bonds, minus 2 dots. So that's a +3 formal charge. And then each of these oxygens are going to have equivalent formal charges because they're all drawn the same way. So 6 minus 1 bond minus 6 dots. So that's a -1 all the way around in this +3. Now if I add those all up, +3 plus -1 plus -1 plus -1, it equals 0. This molecule has no charge to it, so that's okay. Now looking at this second example, for xenon, 8 minus, well, how many bonds have I drawn? 1, 2, 3, 4, minus how many dots? 2. So that's a +2 formal charge. Now these 2 outer oxygens would have identical formal charges because they're bonded the same way. 6 minus 1 minus 6 is -1. So we have a +2 here with a -1 here and -1 here. And then we have that center oxygen, 6 minus 2 minus 4, which would be 0. So again, if I add up all these formal charges, I do get the 0. It still works out. And then this last diagram, where I double bond all the oxygens, like why would you double bond? And you don't want to exceed the octet. Like this middle one exceeds the octet for xenon. This one on the right exceeds the octet for xenon. So look at the xenon on this one. Oops, we have 8 minus 6 bonds minus 2 dots, which is 0. And then each of these oxygens is equivalent in formal charge because they're all bonded the same way. So 6 minus 2 minus 4 is equal to 0. So this is 0, 0, 0, 0. So all of these add up to 0 for their formal charges, but you want the most electronegative element to have the most negative formal charge. You also don't want to exceed the octet if you don't have to. So the first one would be the best one here. For oxygen, because we're just kind of floating that double bond in a couple locations, either of these would be a fine resonance structure because their formal charges were just flipped around. All right, so let's look at this POCl3. start out like that. Phosphorus has 5, oxygen has 6, each chlorine has 7, so that's 21 plus 6 is 27, plus 5 is 32 in my picture. So I've connected with bonds so that I just made 8, so it's 24 that are left. So I can complete these octets. Okay, so let's do formal charge here. Those two chlorines would have equivalent formal charges because they're bonded the same way. So we have 5 minus 4 minus 0 equals plus 1 for the phosphorus. The oxygen would be 6 minus 1 minus 6, which is negative 1. And the chlorines would each be 7 minus 1 minus 6 dots, which is 0. Okay? Now, there are other ways that I could draw this molecule. Like, this is the simplest way, and that's the one you're going to pick. But there are other options. I could take this, because phosphorus has the ability to expand the octet. I could double bond the oxygen to the phosphorus. I still have 32 electrons in this picture, okay? But let's look at the formal charges. The chlorines are all still going to be the same because they're bonded identically. It's just the oxygen is going to change. And the phosphorus. So phosphorus has 5 minus 5 bonds now, minus 0 dots, which is 0. Oxygen would be 6 minus 2 minus 4, which is 0. And then the chlorines would still be 7 minus 1 minus 6, which is 0. So what's wrong with this one? The most electronegative element in my diagram is oxygen, and it doesn't have the most negative formal charge. And also the phosphorus has extended its octet unnecessarily. In the first diagram, the oxygen does have the most negative formal charge. And remember, all of my formal charges are still adding up to 0 because this molecule doesn't have a charge. There is another possibility. I could double bond the chlorine instead. I could have double bonded any of these chlorines. So I'm still not going over 32 electrons. Okay, so let's see how our formal charge changes. Phosphorus, 5 minus 5 minus 0. Oxygen would be 6 minus 1 minus 6. And now the we'll just put a star next to that chlorine. So that chlorine at the top would be 7 minus 2 minus 4. Right, 2 bonds, 4 dots would be plus 1. And the other two chlorines would be 7 minus 1 minus 6, which would be 0. So and that would happen twice because there are two chlorines bonded like that. So I'm still adding up to 0 for my overall. My oxygen still has the most negative formal charge like it should, but I wouldn't pick this because the phosphorus is extending its octet unnecessarily. Okay, so this would be the best structure based on formal charge. This is so fun. It's like a puzzle. I love it, right? You guys are just totally over this. These are a couple other examples, but let's actually just look at this letter D, the xenon tetraoxide. So the xenon would go in the center. We'd throw the oxygens around. So xenon has 8. Each oxygen has 6 times 4 is 24 plus 8 is 32. Now, there are different possibilities here. Because xenon has the ability to expand its octet, we could do this. I still have 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yeah, that still has the same number, the right number of electrons in the diagram. You know, it's still okay in terms of that. Let's look at formal charge on the one on the left. Xenon, 8 minus 4 minus 0. And then each oxygen's identical here, 6 minus 1 minus 6. So there's 4 of them. So that's up to negative 4. So this does that up to 0. I did not extend the octet. Whereas this one we have the oxygen that has the double bond on it, and then the other 3 oxygens that don't. So 8 minus 5 minus 0 is plus 3. Oxygen, the one with the double bond would be 6 minus 2 minus 4. And then each of those other oxygens would be 6 minus 1 minus 6, which is negative 1. And there are 3 of them for negative 3, so that would all add up to 0. So the issue with that would be, I'm expanding my octet unnecessarily. Okay, so this would be my best option. So that's looking at Lewis structures, resonance structures, formal charges. The last thing, and this is super quick, there's really nowhere else to put this, but sometimes you'll see something mentioning bond order. Bond order is just how many bonds are there between these 2 atoms that are bonded together. So a single bond would be a first order bond, a double bond would be a second order bond, and a triple bond would be a third order bond. Thus, the higher the bond order, the stronger the bond is. That is all you need to know about bond order. It's just tuck that away for your Jeopardy debut, I guess. So this would be a bond order of 2. These would be a bond order of 1. This would be a bond order of 3. A 2, a 2, a 1, a 1. So yeah, that's real exciting. That's about it though. Okay, so that's how you determine bond order. So we have gone through resonance structures, we've looked at formal charges, and we've looked at bond order, and we've done a lot in this lesson. So thanks for hanging in there. Catch you on the flip side.